So in a poll I held a while ago, the majority wanted a video that is suitable for home chemistry and something you can do in your own little caves. So some time has passed, I channeled my inner nerd rage and came up with something that hasn't been done before on YouTube and only requires chemicals which most home chemists can get. So starting with acetone, we can eventually make azomethylene, which is a red azodye. The precursor 2,4,6-trimethylaniline is also an important reagent, like for the synthesis of stable carbenes, such as IMAS, which is a common ligand in organometallic chemistry, especially for Grubbs catalysts. But derivatives of IMAS can also be used as a catalyst themselves. But how is that made from acetone, you might ask? Let's dive a little deeper. By using sulfuric acid, acetone can dehydrate into many different products, one of which is mesethylene. We can distill out and purify the mesethylene and then do a mononitration by using sulfuric and nitric acid. This nitro group can then be reduced to an amine by using the simple Béchamp process. In this process, the aromatic nitro group will be reduced to the corresponding aniline, which in this case will yield 2,4,6-trimethylaniline. Then with an oxidative coupling reaction, we can react two of the anilines with each other to form the corresponding diazine product. See, now it doesn't seem so crazy. Anyhow, I did most of these reactions multiple times to get it right, and tried to make sure that they were as accessible and simple as possible. So to get started, I set up a stir plate with an ice bath. I put in a large flask and add in a stir bar. I add in 480 ml of acetone and stir it to cool it down to about 0°C. I attach the thermometer to keep track of the temperature and put a stopper in the other neck. I then attach a dropping funnel and add in 345 ml of 96% sulfuric acid. I slowly add the sulfuric acid to the acetone and make sure to keep the temperature below 10°C. In the reaction, 3 molecules of acetone will react and dehydrate to eventually form mesethylene. This reaction takes many steps, and so produces a lot of side products and tar. At first, 2 molecules of acetone will react and dehydrate to form mesyl oxide or isomesyl oxide. These can then react with another acetone molecule, and then dehydrate again, to for example make phorone. Phorone can directly dehydrate to form mesethylene, but another route via alpha or beta isophorone can also form mesethylene. So there are multiple ways to get to mesethylene. But there's also a lot of other stuff that can be formed. It takes a few hours to add all of the sulfuric acid, and when it's done, I let it stir for about 4 more hours inside of the ice bath, but I don't add in new ice. After that, I take it out of the ice bath and leave it stirring at room temperature for a day. When that is done, I set up a fractional distillation apparatus and start heating the mixture to about 120°C. At one point, gas starts evolving from the mixture, which is mainly sulfur dioxide, mesethylene, and other side products that are distilling over. This should really be done in a fume hood, outside, or with a good trap, because a lot of sulfur dioxide is formed, which is toxic and extremely irritating. I would say it might be one of the worst gases I've had the displeasure to inhale. I removed the fractionating column, because I only put it there in case tar started coming up, but it seems we're safe. I then attach a dropping funnel filled with water, and start steam distilling over all of the mesethylene, by gradually adding in water and distilling it over. The steam will simply carry over mesethylene and other products, without having to heat it strongly. We see a mixture of water and mesethylene with side products coming over, and I continue until I only see pure water coming over. When that is done, we are left with a 2-layer distillate, with water on the bottom and mostly mesethylene on the top. The product still contains a lot of impurities and dissolved sulfur dioxide, so we will have to destroy them. I move it all to a separatory funnel and discard the lower water phase. I then wash the mesethylene layer multiple times with a concentrated sodium hydroxide solution to remove all of the sulfur dioxide. I then wash it with water and put the washed mesethylene layer in a flask inside a heating mantle. I then distill over all of the mesethylene under vacuum with the help of a heat gun. When that is done, all that is left in the flask is some yellow crap, and the distillate is a clear liquid. Now a smell test tells me there are still impurities, which is expected. So to destroy remaining impurities, I add in some sodium metal and reflux it for a few hours. It quickly turned red, and when I returned, it had turned black. I then replace the condenser with a short path distillation apparatus and distill over the mesethylene under a vacuum. Optimally, this should be done with a fractionating column at atmospheric pressure, and only the part that boils around the boiling point of mesethylene should be taken. Anyhow, when everything had distilled over, I destroyed the remaining sodium in the flask by adding ethanol and letting it sit overnight. In the receiving flask, I am left with 42 grams of reasonably pure mesitylene as the distillate, which is a yield of 16%. This is the same as the literature where the yield varies between 13 and 20%. Now that I have mesitylene, I can continue with the mononitration. What I want to do is to nitrate the mesitylene only once, which can be done with sulfuric acid and nitric acid. I tried multiple different ways of doing the nitration to see which one is the best, so you don't have to. So I will quickly show you what doesn't work well, and after that, the procedure that works the best. But first, in the reaction, mesitylene is nitrated under the influence of sulfuric acid and nitric acid to form 2-nitromesitylene and water. In more detail, the nitric acid first reacts with sulfuric acid to form the nitronium ion and water. This nitronium ion can react with the mesitylene double bonds, whereafter water or the bisulfate ion takes up the remaining proton to regenerate the acid. In my first attempt, I followed literature which said they added nitric acid to a cold mixture of mesitylene and sulfuric acid, but they wrote it like they added it relatively quickly. It sounds kinda stupid, but I thought maybe mesitylene is just special. So anyhow, I tried that, but it forms a lot of tar, because the reaction warms up quickly from the addition, which causes a lot of side reactions to happen. So let's see if doing it like these illiterate can still yield some product. After the addition, and then leaving it to stir and cool overnight, I diluted the mixture with water, and added ethyl acetate to extract it. I then washed the extract with brine, and dried it over anhydrous sodium sulfate. I filtered it all through some cotton to remove the sodium sulfate, and then distilled off all of the ethyl acetate to be left with a thick red-black tar. I then set this tar up for distillation to distill out the 2-nitromesitylene. At first, some yellow liquid came over, but I'm not totally sure what this component is. Since the mononitrated product is a solid, it could contain some ethyl acetate and unreacted mesitylene, but it seems a little too much, and this product is yellow. Then, a darker yellow liquid comes over, which solidifies in the flask, which is probably 2-nitromesitylene. Afterward, more product came over, that solidified in the condenser, but this seemed to be the dinitro and trinitro product, since the boiling point was a lot higher. Anyhow, this attempt only yielded a little bit of 2-nitromesitylene, with an absolute horrible purity, so I went back to redo the nitration. In my second attempt, I followed a combination of two procedures, one for the reaction and one for the workup. I again add nitric acid to a mixture of mesitylene and sulfuric acid, but this time I add it slowly and make sure that the temperature stays at or below 10 C. Still, even the tiniest amount of nitric acid that is added to this mixture generates enough heat to sustain nuclear fusion, so it has to be done extremely slowly, which was a huge pain since I had to watch it constantly. Also, midway during the addition, the stirring stopped, because a lot of solid had formed, which made it annoyingly difficult to distribute the heat properly. I tried to loosen it with a glass rod, and diluted the mixture with more sulfuric acid to get it to stir again, but still it stayed quite slow, and the reaction produced more tar, because it was mixing so poorly. When it was done, I poured all into some water to dilute it, and then let it cool down. I then filtered it all through a glass filter with a paper filter on top, and it yielded an off-white solid, which are probably fine particles of the 2-nitromesitylene, making it appear white instead of yellow, though it probably contains some side products as well. I extracted the filtrate with ether and dissolved the whitish solid into ether as well, and then combined them. I then washed the combined ether solutions a few times with a 10% sodium hydroxide solution, which takes out a lot of the tar. I then set the ether layer up for distillation to remove all of the ether, and afterward I was left with a yellow-orange solid. I added 150 ml of a 10% sodium hydroxide solution to the solid, and then opened up a sauna to start steam distilling over the 2-nitromesitylene. Since 2-nitromesitylene is a solid at room temperature, it will usually solidify in the condenser, unless it is supercooling. To make sure it comes through when it solidifies and doesn't block the flow in the condenser, I occasionally turn off the condenser, until all of it liquefies and flows into the receiving flask. When that is done, all that is left in the distilling flask is some tar, and tar dissolved in water. In the receiving flask is a bunch of water, with some solid 2-nitromesitylene. I extracted the solid into some ether, took the ether extract, and set it up for distillation. When pretty much all of the ether is gone, some yellow solid remains, which is 2-nitromesitylene. Unfortunately, the yield of this procedure is also very poor, with only 4.44 grams of product, which is about 8%. The first issue is the large exotherm, when adding nitric acid to the sulfuric acid mesitylene mixture. Even though pretty much everyone in the literature does it this way, it doesn't have to be done that way. Since I already did a toluene nitration before on my channel, I can copy that procedure. Since mixing sulfuric acid and nitric acid itself is already exothermic, I can pre-mix the two acids and allow it to cool down to room temperature, to avoid a large part of the exotherm during the addition. The second issue was the annoyingly long workup, with the filtration, extractions, and steam distillation. So I'm gonna cut that short and directly distill over the 2-nitromethylene, which will also prevent the losses that occur in these steps. So now the final working procedure. I set up a stir plate and a flask and set it in an ice bath. I drop in a stir bar and then add in 42 grams of mesitylene. I then pre-mixed 35 ml of concentrated sulfuric acid and 30 ml of 60% nitric acid. I attach a thermometer to keep track of the temperature, and then a small dropping funnel. After the acid mixture has cooled down to room temperature, I add it to the dropping funnel. I then slowly add the acid mixture to the mesitylene in the flask, while keeping the temperature at or below 10°C. There is barely an exotherm during most of the addition, and I can add it at a normal pace. After a while, there is a slight exotherm, and the temperature increases to 10°C and stays there for some time. The mixture keeps stirring normally, and it doesn't get stuck like before. When the addition was complete, I left it to stir until it cooled down to about 0°C, and then removed the ice bath and left it to stir overnight at room temperature. Afterward, it looked the same. I then set up a stir plate and a beaker, add in about 300 ml of deionized water, and a stir bar. I then pour all of the reaction mixture into the water and wash it with some more water. I then take the diluted mixture and move it all to a separatory funnel. I then start extracting the mixture 3 times with ethyl acetate. During the first extraction, some tar separates out, but it sticks to the glass. I separate the layers and I extract the water layer 2 more times. I then return the combined extracts to the separatory funnel and wash the extracts twice with brine. I then put the washed extract in a beaker and add some anhydrous sodium sulfate to remove remaining water. I then set up a flask and a funnel with some cotton and filter it all through to get rid of the sodium sulfate and any remaining tar. I wash the beaker and the residue once with some more ethyl acetate. I then set the filter up for short path vacuum distillation to distill over all of the ethyl acetate. When the ethyl acetate is gone, I swap the receiving flask and start pulling a strong vacuum. I increase heating and assist the distillation with a heat gun and start distilling over the various components. At first, the unknown yellow liquid distills over as the first component like before. When all of it had come over, I swapped the receiving flask and increased heating. Then 2-nitromethylene started coming over, which solidified in the condenser. To liquefy it again, I stopped the water flow through the condenser and heat it with a heat gun to get it all to come through. When that was done, only some trash remained in the distilling flask, and I was left with 35 grams of 2-nitromethylene as a light yellow solid. This is a lot better and simpler than the previous attempts. The yield can potentially be improved by keeping the temperature during the nitration even lower, and maybe adding a stoichiometric amount of nitric acid, since I used a 10% excess. Anyhow, with this decent yield, I can properly continue with the next step, which is the reduction of the nitro group to an amine. A simple method to do this is with a base champ reduction, which works well to reduce aromatic nitro compounds, and once was the prime method for the reduction of aromatic nitro compounds, but has fallen out of interest because hydrogenation is now the prime method for reducing them. I also tested the reduction with tin 2 chloride and hydrochloric acid, but it was less successful. So I set up a flask in a heating mantle and add in all of the 2-nitromethylene that I made. Since it stuck to the flask, I liquefied with a heat gun and pour it all into the flask. I then add 220 ml of ethanol as a solvent and add in a stir bar. I start stirring and wait for all of the 2-nitromethylene to dissolve. In the meantime, I attach a condenser and a dropping funnel and started heating it to make it go faster. Also, here you see me struggling trying not to get the hose to leak and spray water everywhere. When all of the 2-nitromethylene has dissolved, I add in 45 grams of iron powder, which is the reducing agent in this reaction. I probably should have used a slightly smaller excess, since the iron powder is magnetic and now makes the stir bar too heavy to stir. Let's hope it loosens when it starts reacting. Then to the dropping funnel, I add 170 ml of 37% hydrochloric acid and gradually add it to the flask. It begins to react immediately and the ethanol starts to boil. I keep adding the acid, and after a while the stir bar comes loose again and the mixture turns dark from the iron. In the reaction, iron can reduce the nitro group to an amine in the presence of hydrochloric acid. In detail, this reaction takes multiple steps, but the nitro group is first reduced to a nitroso group, then to an hydroxylamine, and finally to an amine. In all these steps, iron gives up its electrons to get reduced to iron 2 chloride. The iron 2 plus can still participate in another reduction to iron 3 plus, but that is not really relied upon when doing this reaction. When it has all been added, I replace the dropping funnel with a stopper and then reflux the mixture for 2 hours. After that, I let it cool down to room temperature and it has become a mustard yellow slurry because of precipitated salts. Now I need to destroy any remaining acid by adding a base, which will also make sure that the amine is in its free base form so that it can be extracted. So I set up a beaker, drop in a stir bar and add in 200 ml of water and a random amount of sodium hydroxide. I pour all of the reaction mixture into the beaker and a lot more of the iron salts precipitate out. I make sure that the suspension is alkaline by testing with a pH strip, and then move all of the suspension to a separatory funnel in portions and extract out the amine with ethyl acetate. I put the combined extracts in a beaker and add a bunch of anhydrous sodium sulfate to soak up the water and the iron junk that came along with it. I then take this mixture and filter it all through some cotton into another beaker. I then move this filtered in portions to a 1 liter flask and distill off all of the ethyl acetate. When most of the ethyl acetate was gone, it seemed that some of the amine co-distilled with the ethyl acetate, the lower the volume became, even though the amine has quite a high boiling point. At one point, all the ethyl acetate is gone, and thus also the amine stopped coming over with it. A tiny bit of water then distilled over, and I increased the temperature to distill over the amine, but it came over together with some impurities as an orange-red liquid. Afterward, I was left with some clear amine that was mixed with a little bit of ethyl acetate and a red liquid, which is the bulk of the amine with some colored impurities. Using the impure amine would be an absolute disaster for the next reaction, so I will have to purify it somehow. So I went on Discord and asked my YouTube daddy, that chemist, what to do, and he told me to purify it by adding dry hydrochloric acid. So I clamped down the flask with the red liquid and try out some ways to best allow the hydrochloric acid to react with the amine. At first, I thought maybe I can pass it through a needle and bubble it through, but the solid salt quickly plugs the needle. I also tried a needle with a larger borehole, which also didn't work well, and just a syringe, which was also bad. So in the end, I settled for dissolving the mixture back into ethyl acetate, stirring it strongly, and blowing the hydrochloric acid gas on top. This worked very well, and a lot of the salt precipitated out quickly. The full setup is just a flask with a gas connector that contains some sodium chloride, and a dropping funnel with concentrated sulfuric acid on top. The hydrochloric acid is then produced by adding some of the sulfuric acid. The tubing is a small PTFE tube that I secured loosely with some parafilm. Any overpressure would just push up the tubing slightly and vent out of the gas connection through the parafilm. I just let it run for a while, and when it seemed like no more precipitate was forming, I stopped the reaction. It's probably possible to just skip the previous distillation step and form the salt right away, but I haven't tested it. When it's finished, the amine hydrochloric acid salt is in suspension as a white solid, while the non-amine impurities did not precipitate out and stay dissolved in the ethyl acetate. I then set up a flask and a glass filter with a paper filter on top and filter the mixture through while pulling a vacuum. I washed the flask and the residue several times with more ethyl acetate to get out all of the impurities. We see any discoloration in the salt disappear and it becomes as white as my ass in winter. I let it dry on the filter for about 15 minutes and then pour it all into a crystallizing dish. The yield turned out to be 22 grams of what should be mostly 2,4,6-trimethylaniline hydrochloride. At this point, I still smelled ethyl acetate, so it's not completely dry. But after leaving it to dry in the air for about a day, there was no more smell, so the ethyl acetate should be gone. The amine salt should be pretty much odorless. Now for the final reaction, I will have to turn it back into its free base again. I tested out the reaction by using the salt and adding twice as much pyridine, but it seems that the copper bromide catalyst just gets destroyed, since it shouldn't be turning green. I also did the reaction with some impure 2,4,6-trimethylaniline from another run, but it simply didn't form the product. I then tested the reaction with commercial 2,4,6-trimethylaniline to test out the chemistry to see if it works at all, and it did work. So to freebase the amine, I set up a beaker and add in some sodium hydroxide and water. I then add in the amine hydrochloric acid salt and add some more sodium hydroxide until pretty much all of it disappears. I also add in some toluene, which is the reaction solvent, to extract the freebase amine into. I then move it all to a separatory funnel and separate the layers. I extract the water layer a few more times with toluene and then combined all the toluene extracts in a beaker. I add some anhydrous sodium sulfate to remove the water droplets that came along, and then filter it through some cotton, directly into the flask I will be using for the reaction. I wash the beaker and cotton a few more times with a little bit of toluene, and when that is done, I add 2.4 ml of pyridine to the solution. Then I add 0.15 grams of copper 1 bromide as the catalyst. The mixture almost immediately turns yellow, and becomes darker over time. I add a condenser and a septum, and through the septum, I stick a needle which is connected to the exhaust of a vacuum pump, and I slowly blow air through the mixture constantly, because the reaction requires oxygen. I start heating the mixture to a reflux and leave it for a few hours. In the reaction, the catalyst allows for oxidative coupling between the two aromatic amines, to form the corresponding azo compound. In detail, the pyridine and oxygen react with the copper 1 atoms, to form a coordination complex, in which the barrier for oxygen to react with the anilines is lowered. So it allows for the oxygen to react with the anilines, the split of two water molecules, and couple the nitrogens to form a diazine group. When I come back, it should be finished, and the mixture has turned black. I then remove all of the adapters and attach a short path distillation apparatus to remove the toluene under a vacuum. When all of the toluene is gone, a dark red to black liquid is left behind. I add some DCM to dissolve the product and set it aside for a second. To purify the product, I have to do column chromatography, but the separation will be extremely simple. So I can just half-ass a column without caring too much about doing it perfectly. And it's a great way to get started with column chromatography, if you have never done it before, since it won't really matter if you mess up slightly. So I set up a column and add in 200 grams of silica gel that I mix with a few hundred mils of 5% ethyl acetate in hexanes. I've put on a crappy uneven layer of sand and let the solvent run into it. And now I just pour all of the product DCM mixture on top, without caring too much about trying to do it perfectly. I run the product through and then pour a bunch of the eluent on top, and run the column by occasionally adding pressure on top with the exhaust of a vacuum pump, by turning it on and off for a split second. We can visually see the red product separating, and it's the first component that comes off the column. You don't even need to check with TLC, since you can just see when it comes through. I simply collect the red product and then stop the column, and discard the rest. I then set up a flask, and we can clearly see the red product in solution. I pour all of it into the flask and set it up for short path vacuum distillation to remove all of the solvent. Afterward, a red solid is left behind, and I then pull a vacuum directly on the flask to make sure all of the solvent is gone. When that is done, I am left with a sad quantity of a dark red solid, which should be azomethylene, which is also said to be red in literature. Now to get it all together and off the stir bar, I dissolve it again in some DCM, and we can clearly see its blood red color. I leave it to evaporate in the air, and when I come back, it is all collected on the side and formed some crystals. The yield turned out to be 0.13 grams, which is a sad 3%. But at least there is something. Since the reaction required oxygen, it would probably be best to supply pure oxygen instead of air, since the CO2 in air can react with amines to form carbamates, which can go do other funky stuff. And as we have seen, the reaction is fairly sensitive to the purity of the amine. Also, I tested to see if this compound is photo-switchable, like many azobenzenes are said to be, but I tried blasting it with a UV light and with visible light, and it didn't seem to change color, so that's unfortunate. I challenge anyone to get a better yield than me, which honestly shouldn't be too hard with the mentioned improvements. But if anyone replicates this, you don't have to make the Azodye, because 2,4,6-trimethylaniline is also useful for making carbenes, which are also fun. Now that I have a dye, it would only be fitting if I dyed something with it. At least, that is what I was forced to do against my will. I didn't have any white socks, so I had to use these random grey ones. But I wanted white socks, so I will try to bleach them first. I'm not a tie-dye channel, so I don't know what the hell I'm supposed to do. So I'm just gonna put them in bleach, and hopefully it will turn white. I asked my mom for bleach, and then put the socks in a dish. I put some bleach on them, and apparently it's slimy, which I didn't know since I literally never used bleach. Is that weird? I dilute it with some water, mix it around, and add some more bleach until it is all submerged. I let it sit for about 20 minutes, but it really doesn't whiten that much, so my day is ruined. I then tried to bleach it with some 10% hydrogen peroxide, but that shit ain't working either. So I tried adding some more 50% peroxide, but I couldn't see if it was doing anything. I then tried to heat it, but that didn't seem to do much either. And afterward, I just put them on a hot plate to dry, and blasted with a heat gun to make it go faster. But it started smoking a bit too much, so I think I burned it, and there's also a hole. After a while, it is dry enough, and I guess I have a wider pair of socks now. I then set up a dish again, and take all of the azomethylene and put it inside. I then add some DCM to dissolve it, and put in one sock to soak it all up. Okay, I guess that kinda worked. Now I will just dry it with a heat gun to remove all of the DCM. After a while, most of the DCM is gone, and I am left with a very beautiful carcinogenic orange sock. The yield turned out to be 100%. Anyhow, that was it for this video. Thanks for watching, and as always, a special thanks to all my patrons. See ya.